Welcome back to the channel. Today's a good one. So I will be walking you through how to draw an electrochemical cell, as well as all the sort of subsequent questions you could be asked, like determining the cell voltage, so the EMF, the overall redox equation for the cell, and then the cell statement. So this is a complete start to finish guide for these electrochemical cell questions. So it says construct an electrochemical cell between systems 1 and 2, determine the cell voltage, redox equation, and cell statement. So in the previous videos I said, when you're drawing these cells, these overall electrochemical cells, you must make sure that the most negative half cell, in this case it's number 1, is on the left, and the most positive one goes on the right. The second thing to say is the most negative half cell is always oxidized, and the most positive one is reduced. That means the half cell that is being oxidized must be written in reverse. So iron solid is oxidized to Fe2 plus 2 electrons. So just to recap that point, the most negative half cell goes on the left, the most positive one goes on the right, and the most negative half cell represents an oxidation. So let's begin the sketch, and what I like to do is write the half equation underneath the cell to remind me. So Fe2 plus 2E, and then on the right hand side we have the other half cell, which is the vanadium species, the VO2 plus, and that's been oxidized, been reduced to V3 plus. Okay, so the electrode on the left hand side, you can see that it involves solid iron, so that's going to be the electrode, and then in the electrolyte there will be the Fe2 plus ion that is produced. The electrons are going to be made on this left hand side as the iron is oxidized. They will flow along the wire. There will be a voltmeter where we can read off the voltage, and then they'll flow into the right hand side, where the electrode we need for this one is going to be platinum. Now the reason why it's platinum is because the half cell we're investigating has aqueous species, and obviously you can't have a liquid electrode. It needs to be a solid metal conductor, so the choice is platinum. And the reason why platinum is picked is because, number 1, it's an excellent conductor of electricity. Number 2, it's chemically inert. So if you remember from GCSE and lower school science, that platinum is at the bottom of the reactivity series of metals. And number 3, it works really well with like gaseous electrodes because of its large surface area and absorbs electrons really well. So a few reasons there. So platinum, and then in the electrolyte will be the two ions VO2 plus and then V3 plus. So as I just said, the electrons are going to be made on the left, they're going to flow this way and into the right. So as the left hand side is generating the electrons, this is therefore the negative terminal, and the right hand side must therefore be the positive terminal of the cell. Okay, finally is to connect the two half cells with a salt bridge, which is this green line here. The salt bridge can be made up of any sort of group 1 salt, so NaCl, potassium nitrate, anything that is soluble in water. And what it does is it allows the passage of ions between the half cells without them having to mix, so it completes the circuit. Okay, finally is the discussion of the conditions for a cell. It's 298 Kelvin. It's always 1 atm pressure, so atmospheric pressure, for the solutions involved. So 1 mole per decimeter cubed. So that's the standard concentration for any solutions involved. Okay, providing you have drawn the cell in the way that I've described, in this exact way, then working out the E cell voltage is very, very simple. All you have to do is use this equation. So E cell, voltage of the half cell on the right, take away the one on the left, providing you have set it up in the way that I've just described. You don't change the signs of these numbers, you don't rearrange anything, you just literally plug the numbers in and get the answer. It's very straightforward. So the one on the right is the vanadium, minus 0.44 is going to give me an answer of plus 0.78 volts. So we would read on the voltmeter 0.78 volts for this particular cell. Next is the overall redox equation. So the way to create redox equations is you must make sure that the electrons are balanced before you add the half equations together. If you look at the vanadium half equation, if I just circle the bit that's we need to address, you can see there's one electron in the vanadium half cell but there's 2 in the ion. That means to make the electrons the same, I have to multiply this one through by 2, so the electrons are the same and then they cancel when they come to be added together. Fe goes to Fe2 plus 2e minus. Then the vanadium one, let me just check that's everything. Yes, it is. And then you draw a line and you literally add the 2 together like a sum in maths. Everything to the left and then everything to the right hand side. So on the left hand side we have Fe plus 2VO2 plus 4H plus 2E. Then on the right hand side we have Fe2 plus 2V3 plus 2H2O plus 2 electrons. And immediately we can see we can cancel out the electrons left and right, which leaves us with Fe plus 2VO2 plus 4H plus goes to Fe2 plus 2V3 plus 2 waters. And then you can quickly check that the atoms are balanced, which they are, but also that the charges are balanced. So if we look at the left hand side, this is an important one because it's sometimes very easy to balance the equation but not the charges. So we have 2 times plus 2 is plus 4 here, plus another 4 there gives a total of plus 8 on the left hand side. Then on the right hand side we have plus 2 there, and then 2 times plus 3 is plus 6. So again that comes to plus 8. So plus 8 on the right, plus 8 on the left. So that confirms our equation is definitely correct. Finally is the cell statement. So the cell statement, so this mentioned here, is an abbreviated form of the overall cell reaction. And all you show is the main changes in state of the species being oxidized and reduced. And you must include state symbols in this, as it is basically an exercise in state symbols. I have described this in detail in one of my other videos, so please check that out if you haven't watched it. But just a quick recap: if you use a solid line between different things, that means a change in state. And if you use a comma, like that means 2 species that are in the same state. So let's take a look at the final answer. So we have, on the left hand side, Fe is a solid that is being oxidized to Fe2 plus. So there's the solid line. Then what you usually see is a double dash or double solid line indicating the salt bridge. And then on the right hand side you have the species that are being reduced. So it's the VO2 plus AQ, but because that's in the same phase as the V3 plus being formed, we just use a comma, and then it's 2V3 plus, and then that reduction takes place on a platinum electrode for the reasons that I said earlier on. So I use a solid line and I get PTS. And that's it. The 4 main things from an electrochemical cell question: how to draw the cell, how to work out the cell voltage, how to write the overall electrochemical cell / redox reaction, and then finally the cell statement. That's it for today. I hope you found this helpful. Please like and subscribe and check out the other content that I've made. I'm sure you're going to get some value from it, and I will see you in the next one.